Welcome to solverfy.
In this problem, we have an electron which is trapped in a one-dimensional infinite potential well. The length of the width of the well in this case is 3 meters. So we can write this as 3 into 10 power 9 nanometers. Like we are purposely writing it this way instead of 3 meters, and that is 3 meters. The energy of electron in an infinite potential well is given as n square h square over 8 ml square. Now we need to find the energy difference between the electron's ground state and its first excited state. So A is E2 minus E1. E1 is the ground state energy and E2 is the first excited state energy. This will be equal to 2 square minus 1, which is 3. So 3h square over 8 ml square. We can substitute for the mass of electron with L. H can be taken as, instead, let's call it hc instead. We can multiply and divide by c in the numerator and denominator. It's 1240 electron volt nanometer. So the value of this comes out as 1.3 into 10 to the power minus 19 electron volts. As you can see, the energy difference between E2 and E1 is very small. So we need to find out now what should be the quantum state En such that En plus 1 minus En is ultimately equal to 1 eV. Between the ground state and the first excited state, the energy difference is hardly there. But what should be the energy difference? What levels do we need in order to have an energy difference of at least 1 eV? Now, this is again equal to h square over 8 ml square. We have n plus 1 whole square minus n square. Now that's equal to n square into 2n plus 1 over 8 ml square. Substituting all the values, we find that n is equal to 4 mc square. So we divide and subtract by c square into L square. Let's call this value as delta E whole divided by hc whole square. This ultimately leads to the fact that n should be equal to 1.2 into 10 power 19. So you see the value of n is very large. It is almost 10 power 19. So the quantum number in this case is 10 power 19. Now we need to find that at what quantum number, at this quantum number. So if n is equal to 1.2 into 10 power 19, we need to find what multiple of electrons rest energy would give the energy at this rate. So we simply need to evaluate the fraction between En over mc square. Mc square is the rest energy of the electron and En is the energy of the electron in this given state. Now this can easily be done. We can again substitute for the value of n square h square over 8 ml square divided by mc square, and substituting all the values, we just this number, the value of this is 6 into 10 power 18 electron volts, and this is divided by the mass of electron into c square, which is 511 keVs, so that is 10 power 3 eV, such that this is equal to 1.2, so the ratio is 1.2 into 10 power 13. This is part C. For the last question, we are asked if this electron is relativistic. As we can see that the fraction of En versus mc square is much greater than 1. This implies that the energy of electron in this case is much greater than its rest energy. So this electron is relativistic. So the electron in this case is